There's some special cases of cash flow diagrams that don't look like a uniform series. For example, we might have a cash flow diagram that grows like this. Instead of a uniform series of payments, we have a growing series of payments. And in this example, the growth is linear. What would that look like? It would be an agreement between two people in a contract, perhaps a landlord and a tenant, in which they agree that the rent is going to go up by the same amount every year. Perhaps they add $100, perhaps they add whatever the constant amount is. So from time equals 0, we have this linearly increasing cash flow diagram or series of payments that go off into future time. We can take a cash flow diagram and split it into components. It could have, for example, a uniform series component that we would call A. It could have a present value component. It could have some future value component, and it could have this linear component. We're going to call the linear component G. G equals the linear growth in this triangular portion of the cash flow diagram. And the way that we would treat this cash flow diagram is have a separate formula for F to present value, a separate formula for A to present value, which we looked at in the previous videos, and now another separate formula for G to present value, so that P equals the G times that factor plus A times the present worth formula factor for an annuity or a uniform series plus F times the factor for the present worth factor for a future payment. We handled F and A in previous videos, so we're going to look more closely at this linear increasing cash flow diagram. And as you might expect, there's an equation that goes with that. Once you know the growth rate, you multiply it by the quantity 1 plus the interest rate raised to the number of compounding periods minus the term the interest rate times the number of compounding periods minus 1 all over the interest rate squared times the quantity 1 plus the interest rate raised to the number of compounding periods. What does this do? It calculates only the portion of the cash flow diagram that is contained within this triangle. It assumes that the cash flow diagram starts at the first compounding period at 0 and increases the constant amount G in dollars per year thereafter. If there are other more complicated components of the cash flow diagram, for example, the rent in the first year is $1,000, and in the second year it's $1,200, G would be 200, the amount of the increase in the rent. But we'd have to use the A formula, the uniform series formula, to calculate the present value of this portion of the cash flow diagram. And if there were a future balloon payment at the end of the lease, then we would have to use the F present worth factor to calculate the present worth of that one. In this cash flow diagram, we have 3 components: the G component, linear increase, the A component, uniform series, and the F component of future value. And they can all be reduced to the present worth using their respective present worth factors. Here's the present worth factor for what is called an arithmetic gradient series. Now, the arithmetic gradient series is interesting, and there might be applications of it, but in the next video I'm going to show you the geometric gradient series, which is more common.